In astronomy, Kepler's laws of planetary motion are three scientific laws describing the motion of planets around the Sun. The orbit of a planet is an ellipse with the Sun at one of the two foci. A line segment joining a planet and the Sun sweeps out equal areas during equal intervals of time. The square of the orbital period of a planet is directly proportional to the cube of the semi-major axis of its orbit. Most planetary orbits are nearly circular, and careful observation and calculation are required in order to establish that they are not perfectly circular. Calculations of the orbit of Mars indicated an elliptical orbit. From this, Johannes Kepler inferred that other bodies in the Solar System, including those farther away from the Sun, also have elliptical orbits. Kepler's work, published between 1609 and 1619, improved the heliocentric theory of Nicolaus Copernicus, explaining how the planet's speeds varied, and using elliptical orbits rather than circular orbits with epicycles. Isaac Newton showed in 1687 that relationships like Kepler's would apply in the Solar System to a good approximation, as a consequence of his own laws of motion and law of universal gravitation. Comparison to Copernicus. Kepler's laws improved the model of Copernicus. If the eccentricities of the planetary orbits are taken as zero, then Kepler basically agreed with Copernicus. The planetary orbit is a circle. The Sun is at the center of the orbit. The speed of the planet in the orbit is constant. The eccentricities of the orbits of those planets known to Copernicus and Kepler are small, so the foregoing rules give fair approximations of planetary motion, but Kepler's laws fit the observations better than does the model proposed by Copernicus. Kepler's corrections are not at all obvious. The planetary orbit is not a circle, but an ellipse. The Sun is not at the center but at a focal point of the elliptical orbit. Neither the linear speed nor the angular speed of the planet in the orbit is constant, but the area speed, closely linked historically with the concept of angular momentum, is constant. The eccentricity of the orbit of the Earth makes the time from the March equinox to the September equinox, around 186 days, unequal to the time from the September equinox to the March equinox, around 179 days. A diameter would cut the orbit into equal parts, but the plane through the Sun parallel to the equator of the Earth cuts the orbit into two parts with areas in a 186 to 179 ratio, so the eccentricity of the orbit of the Earth is approximately approximately equals pi 4 186 minus 179 186 plus 179 approximately equals 0.015. Display style approximately frac pi 4 frac 186 to 179 186 plus 179 approximately 0.015, which is close to the correct value 0.016710219. See Earth's orbit. The calculation is correct when perihelion, the date the Earth is closest to the Sun, falls on a solstice. The current perihelion, near January 3, is fairly close to the solstice of December 21 or 22. Nomenclature. It took nearly 2 centuries for the current formulation of Kepler's work to take on its settled form. Voltaire's Elements de la philosophie de Newton, Elements of Newton's Philosophy of 1738 was the first publication to use the terminology of «laws». The Biographical Encyclopedia of Astronomers in its article on Kepler p. 620 states that the terminology of scientific laws for these discoveries was current at least from the time of Joseph de Lalande. It was the exposition of Robert Small, in an account of the astronomical discoveries of Kepler 1814, that made up the set of 3 laws, by adding in the third. Small also claimed, against the history, that these were empirical laws, based on inductive reasoning. Further, the current usage of Kepler's second law is something of a misnomer. Kepler had 2 versions, related in a qualitative sense, the «distance law» and the «area law». The «area law» is what became the second law in the set of 3, but Kepler did himself not privilege it in that way. History. Johannes Kepler published his first 2 laws about planetary motion in 1609, having found them by analyzing the astronomical observations of Tycho Brahe. Kepler's third law was published in 1619. Kepler had believed in the Copernican model of the Solar System, which called for circular orbits, but he could not reconcile Brahe's highly precise observations with a circular fit to Mars' orbit, Mars coincidentally having the highest eccentricity of all planets except Mercury. His first law reflected this discovery. Kepler in 1621 and Godefroy Wendelin in 1643 noted that Kepler's third law applies to the 4 brightest moons of Jupiter. The second law, in the «area law» form, was contested by Nicolaus Mercator in a book from 1664, but by 1670 his philosophical transactions were in its favor. As the century proceeded, it became more widely accepted. The reception in Germany changed noticeably between 1688, the year in which Newton's Principia was published and was taken to be basically Copernican, and 1690, by which time work of Gottfried Leibniz on Kepler had been published. Newton was credited with understanding that the second law is not special to the inverse square law of gravitation, being a consequence just of the radial nature of that law, while the other laws do depend on the inverse square form of the attraction. Carl Runge and Wilhelm Lenz much later identified a symmetry principle in the phase space of planetary motion, the orthogonal group O acting, which accounts for the first and third laws in the case of Newtonian gravitation, as conservation of angular momentum does via rotational symmetry for the second law. Formulary. The mathematical model of the kinematics of a planet subject to the laws allows a large range of further calculations. First law of Kepler: the orbit of every planet is an ellipse with the Sun at one of the 2 foci. Mathematically, an ellipse can be represented by the formula r equals p1 plus epsilon cos theta. Display style r equals frac p1 plus var epsilon cos theta, where p display style p is the semi-lattice rectum, epsilon is the eccentricity of the ellipse, r is the distance from the Sun to the planet, and theta is the angle to the planet's current position from its closest approach, as seen from the Sun. So r, theta are polar coordinates. For an ellipse 0 at theta equals 0 degrees, perihelion, the distance is minimum r min equals p 1 plus epsilon. Display style r underscore min equals frac p 1 plus var epsilon at theta. Topic 90 degrees and at theta. 270 degrees. The distance is equal to p display style p at theta equals 180 degrees, aphelion, the distance is maximum. By definition, aphelion is, invariably, perihelion plus 180 degrees r max equals p1 minus epsilon display style r underscore max equals frac p1 var epsilon. The semi-major axis A is the arithmetic mean between rmin and r max minus a equals a minus r min equals p1 minus epsilon 2 display style begin aligned r underscore max a and equals a r underscore min 3 pt o and equals frac p1 var epsilon caret 2 end aligned. The semi-minor axis B is the geometric mean between rmin and r max B equals br min B equals p1 minus epsilon 2 display style begin aligned frac r underscore max B and equals frac B r underscore min 3 pt B and equals frac p sqrt 1 var epsilon caret 2 end aligned. The semi-lattice rectum P is the harmonic mean between rmin and r max. 1 r min minus 1 p equals 1 p minus 1 r max p a equals r max r min equals b2 display style begin aligned frac 1 r underscore min frac 1 p and equals frac 1 p frac 1 r underscore max 3 pt pa and equals r underscore max r underscore min equals b caret 2 end aligned. The eccentricity epsilon is the coefficient of variation between rmin and r max. Epsilon equals r max minus r max plus r min. Display style var epsilon equals frac r underscore max r underscore min r underscore max plus r underscore min. The area of the ellipse is a equals pi ab. Display style a equals pi ab. The special case of a circle is epsilon. Topic 0 resulting in r p. Topic rmin r max. Topic a b and a. equals pi r2 equals. Topic: Second law of Kepler equals. A line joining a planet and the Sun sweeps out equal areas during equal intervals of time. The orbital radius and angular velocity of the planet in the elliptical orbit will vary. This is shown in the animation. The planet travels faster when closer to the Sun, then slower when farther from the Sun. Kepler's second law states that the blue sector has constant area. In a small time d t dt, the planet sweeps out a small triangle having base line r r and height r d theta r d theta and area d a equals 1 2 r r d theta. Display style da equals frac 1 2 cdotr d theta, and so the constant areal velocity is d a d t equals 1 2 r 2 d theta d t. Display style frac da dt equals frac 1 2 r caret 2 frac d theta dt. The area enclosed by the elliptical orbit is pi a b. Display style pi ab. So the period p display style p satisfies p 1 2 r 2 d theta d t equals pi a b. Display style p cdot frac 1 2 r caret 2 frac d theta dt equals pi ab, and the mean motion of the planet around the Sun n equals 2 pi p. Display style n equals frac 2 pi p satisfies r 2 d theta equals a b n d t. Display style r caret 2 d theta equals abn dt. Topic: Third law of Kepler. The square of the orbital period of a planet is directly proportional to the cube of the semi-major axis of its orbit. This captures the relationship between the distance of planets from the Sun, and their orbital periods. Kepler enunciated in 1619 this third law in a laborious attempt to determine what he viewed as the music of the spheres according to precise laws, and express it in terms of musical notation. So it was known as the harmonic law. Using Newton's law of gravitation, published 1687, this relation can be found in the case of a circular orbit by setting the centripetal force equal to the gravitational force m r omega 2 equals g m m r 2. Display style Mr omega caret 2 equals g frac r caret 2. Then, expressing the angular velocity in terms of the orbital period and then rearranging, we find Kepler's third law m r 2 pi t 2 equals g m m r 2 t 2 equals 4 pi 2 g m r 3 t 2 r 3. Display style Mr left frac 2 pi t right caret 2 equals g frac r caret 2 right arrow t caret 2 equals left frac 4 pi caret 2 gm right r caret 3 right arrow t caret 2 propto r caret 3. A more detailed derivation can be done with general elliptical orbits, instead of circles, as well as orbiting the center of mass, instead of just the large mass. This results in replacing a circular radius r r with the elliptical semi-major axis a, as well as replacing the large mass m m with m plus m m plus m. However, with planet masses being so much smaller than the Sun, this correction is often ignored. The full corresponding formula is a 3 t 2 equals g m plus m 4 pi 2 approximately equals g m 4 pi 2 approximately equals 7.496 10 minus 6 3 days 2 is constant. Display style frac a caret 3 t caret 2 equals frac g m plus m 4 pi caret 2 approximately frac g m 4 pi caret 2 approximately 7. 496 CDOT 10 caret -6 left frac text O caret 3 text days caret 2 right text is constant, where m display style m is the mass of the Sun. M display style m is the mass of the planet, and g display style g is the gravitational constant. T display style t is the orbital period, and a display style a is the elliptical semi-major axis. The following table shows the data used by Kepler to empirically derive his law. Upon finding this pattern, Kepler wrote, "For comparison, here are modern estimates." Topic: Planetary acceleration. Isaac Newton computed in his Philosophiae Naturalis Principia Mathematica the acceleration of a planet moving according to Kepler's first and second law. The direction of the acceleration is towards the Sun. The magnitude of the acceleration is inversely proportional to the square of the planet's distance from the Sun, the inverse square law. This implies that the Sun may be the physical cause of the acceleration of planets. However, Newton states in his Principia that he considers forces from a mathematical point of view, not a physical, thereby taking an instrumentalist view. Moreover, he does not assign a cause to gravity. Newton defined the force acting on a planet to be the product of its mass and the acceleration. See Newton's laws of motion. So, every planet is attracted towards the Sun. The force acting on a planet is directly proportional to the mass of the planet and is inversely proportional to the square of its distance from the Sun. The Sun plays an unsymmetrical part, which is unjustified. So he assumed, in Newton's law of universal gravitation, all bodies in the Solar System attract one another. The force between two bodies is in direct proportion to the product of their masses and in inverse proportion to the square of the distance between them. As the planets have small masses compared to that of the Sun, the orbits conform approximately to Kepler's laws. Newton's model improves upon Kepler's model, and fits actual observations more accurately. See two-body problem. Below comes the detailed calculation of the acceleration of a planet moving according to Kepler's first and second laws. Topic: Acceleration vector. From the heliocentric point of view, consider the vector to the planet r equals r caret display style math r equals r hat math r, where r display style r is the distance to the planet and r caret display style hat math r is a unit vector pointing towards the planet. D r caret d t equals r caret equals theta caret d theta caret d t equals theta caret equals minus theta r caret display style frac d h at math BF R dt equals dot hat math BF R equals dot theta hat bold symbol theta q quad frac d hat bold symbol theta dt equals dot hat bold symbol theta equals dot theta hat math BF R, where theta caret display style hat bold symbol theta is the unit vector whose direction is 90 degrees counterclockwise of r caret display style hat math BF R and theta display style theta is the polar angle, and where a dot on top of the variable signifies differentiation with respect to time. Differentiate the position vector twice to obtain the velocity vector and the acceleration vector r equals r caret plus r caret equals r caret plus r theta caret r equals r caret plus r caret plus r theta caret plus r theta caret plus r theta caret equals r minus r theta 2 r caret plus r theta plus 2r theta caret display style begin aligned dot math BF R and equals dot r hat math BF R plus r dot hat math BF R equals dot r hat math BF R plus r dot theta hat bold symbol theta ddot math BF R and equals left ddot r hat math BF R plus dot r dot hat math BF R right plus left dot r dot theta hat bold symbol theta plus r ddot theta hat bold symbol theta plus r dot theta dot hat bold symbol theta right equals left ddot r dot theta caret 2 right hat math BF R plus left r ddot theta plus 2 dot r dot theta right hat bold symbol theta end aligned. So r equals a r caret plus a theta caret display style ddot math BF R equals a underscore r hat bold symbol r plus a underscore theta hat bold symbol theta, where the radial acceleration is a r equals r minus r theta 2 display style underscore r equals ddot r dot theta caret 2, and the transversal acceleration is a theta equals r theta plus 2 r theta. Display style underscore theta equals r ddot theta plus 2 dot r dot theta. Topic: Inverse square law. Kepler's second law says that r 2 theta equals n a b display style r caret 2 dot theta equals nab is constant. The transversal acceleration a theta display style underscore theta is 0 d r 2 theta d t equals r 2 r theta plus r theta equals r a theta equals 0. Display style frac d left r caret 2 dot theta right dt equals r left 2 dot r dot theta plus r d dot theta right equals raw underscore theta equals 0. So the acceleration of a planet obeying Kepler's second law is directed towards the Sun. The radial acceleration a r display style underscore text r is a r equals r minus r theta 2 equals r minus r n a b r 2 equals r minus n 2 a 2 b 2 r 3. Display style underscore text r equals ddot r dot theta caret 2 equals ddot r left frac nab r caret 2 right caret 2 equals ddot r frac n caret 2 a caret 2 b caret 2 r caret 3. Kepler's first law states that the orbit is described by the equation p r equals 1 plus epsilon cos theta. Display style frac p r equals 1 plus var epsilon cos theta. Differentiating with respect to time minus P R 2 equals minus epsilon sin theta display style frac p dot r caret 2 equals var epsilon sin theta dot theta, or p r equals n a b epsilon sin theta display style p dot r equals nab var epsilon sin theta. Differentiating once more, p r equals n a b epsilon cos theta equals n a b epsilon cos theta n a b r 2 equals n 2 a 2 b 2 r 2 epsilon cos theta display style p d dot r equals nab var epsilon cos theta dot theta equals nab var epsilon cos theta frac nab r caret 2 equals frac n caret 2 a caret 2 b caret 2 r caret 2 var epsilon cos theta. The radial acceleration a r display style a underscore text r satisfies p a r equals n 2 a 2 b 2 r 2 epsilon cos theta minus p n 2 a 2 b 2 r 3 equals n 2 a 2 b 2 r 2 epsilon cos theta minus p r display style pa underscore text r equals frac n caret 2 a caret 2 b caret 2 r caret 2 var epsilon cos theta p frac n caret 2 a caret 2 b caret 2 r caret 3 equals frac n caret 2 a caret 2 b caret 2 r caret 2 left var epsilon cos theta frac p r right. Substituting the equation of the ellipse gives p a r equals n 2 a 2 b 2 r 2 p r minus 1 minus p r equals minus n 2 a 2 r 2 b 2 display style pa underscore text r equals frac n caret 2 a caret 2 b caret 2 r caret 2 left frac p r minus 1 frac p r right equals frac n caret 2 a caret 2 r caret 2 b caret 2. The relation b 2 equals p a display style b caret 2 equals pa gives the simple final result a r equals minus n 2 a 3 r 2 display style a underscore text r equals frac n caret 2 a caret 3 r caret 2. This means that the acceleration vector r display style math BF ddot r of any planet obeying Kepler's first and second law satisfies the inverse square law r equals minus alpha r 2 r caret display style math BF ddot r equals frac alpha r caret 2 hat math BF r, where alpha equals n 2 a 3 display style alpha equals n caret 2 a caret 3 is a constant, and r caret display style hat math BF r is the unit vector pointing from the Sun towards the planet, and r display style r is the distance between the planet and the Sun. According to Kepler's third law, alpha display style alpha has the same value for all the planets. So the inverse square law for planetary accelerations applies throughout the entire solar system. The inverse square law is a differential equation. The solutions to this differential equation include the Keplerian motions, as shown, but they also include motions where the orbit is a hyperbola or parabola or a straight line. See Kepler orbit. Newton's law of gravitation. By Newton's second law, the gravitational force that acts on the planet is F equals m planet r equals minus m planet alpha r minus 2 r caret Display style Math F equals M underscore text planet Math DDOT R equals M underscore text planet alpha R caret -2 hat Math R, where M planet display style M underscore text planet is the mass of the planet, and alpha display style alpha has the same value for all planets in the solar system. According to Newton's third law, the Sun is attracted to the planet by a force of the same magnitude. Since the force is proportional to the mass of the planet, under the symmetric consideration, it should also be proportional to the mass of the Sun. M Sun display style M underscore text Sun. So alpha equals G M Sun display style alpha equals gm underscore text Sun, where G display style G is the gravitational constant. The acceleration of solar system body number I is, according to Newton's laws, r I equals G J does not equal I M J R I J minus 2 R caret I J display style Math DDOT R underscore I equals G sum underscore J NEQI M underscore J R underscore I J caret -2 hat Math R underscore I J, where M J display style M underscore J is the mass of body J R I J display style R underscore I J is the distance between body I and body J R caret I J display style hat Math R underscore I J is the unit vector from body I towards body J, and the vector summation is over all bodies in the solar system besides I itself. In the special case where there are only two bodies in the solar system, Earth and Sun, the acceleration becomes r Earth equals G M Sun R Earth Sun minus 2 R caret Earth Sun display style Math DDOT R underscore text Earth equals GM underscore text Sun R underscore text Earth text Sun caret -2 hat Math R underscore text Earth text Sun, which is the acceleration of the Kepler motion. So this Earth moves around the Sun according to Kepler's laws. If the two bodies in the Solar System are Moon and Earth, the acceleration of the Moon becomes r Moon equals G m Earth r Moon Earth minus 2 r caret Moon Earth. Display style Math DDOT R underscore text Moon equals GM underscore text Earth R underscore text Moon text Earth caret -2 hat Math R underscore text Moon text Earth. So in this approximation, the Moon moves around the Earth according to Kepler's laws. In the three-body case the accelerations are r Sun equals g m Earth r Sun Earth minus 2 r caret Sun Earth plus g m Moon r Sun Moon minus 2 r caret Sun Moon r Earth equals g m Sun r Earth Sun minus 2 r caret Earth Sun plus g m Moon r Earth Moon minus 2 r caret Earth Moon r Moon equals g m Sun r Moon Sun minus 2 r caret Moon Sun plus g m Earth r Moon Earth minus 2 r caret Moon Earth display style begin aligned Math DDOT R underscore text Sun and equals GM underscore text Earth R underscore text Sun text Earth caret -2 hat Math R underscore text Sun text Earth plus GM underscore text Moon R underscore text Sun text Moon caret -2 hat Math R underscore text Sun text Moon Math DDOT R underscore text Earth and equals GM underscore text Sun R underscore text Earth text Sun caret -2 hat Math R underscore text Earth text Sun plus GM underscore text Moon R underscore text Earth text Moon caret -2 hat Math R underscore text Earth text Moon Math DDOT R underscore text Moon and equals GM underscore text Sun R underscore text Moon text Sun caret -2 hat Math R underscore text Moon text Sun plus GM underscore text Earth R underscore text Moon text Earth caret -2 hat Math BF R underscore text Moon text Earth end aligned. These accelerations are not those of Kepler orbits, and the three-body problem is complicated. But Keplerian approximation is the basis for perturbation calculations. See lunar theory. Topic: Position as a function of time. Kepler used his two first laws to compute the position of a planet as a function of time. His method involves the solution of a transcendental equation called Kepler's equation. The procedure for calculating the heliocentric polar coordinates r, theta of a planet as a function of the time t since perihelion, is the following four steps. Compute the mean anomaly m equals nt, where n is the mean motion. N p equals 2 pi. Display style n CDOT p equals 2 pi radians, where p is the period. Compute the eccentric anomaly E by solving Kepler's equation. M equals E minus epsilon sin E. Display style m equals E var epsilon sin E. Compute the true anomaly theta by the equation 1 minus epsilon tan 2 theta 2 equals 1 plus epsilon tan 2 e 2. Display style 1 var epsilon tan caret 2 frac theta 2 equals 1 plus var epsilon tan caret 2 frac e 2. Compute the heliocentric distance r equals a 1 minus epsilon cos E. Display style r equals a 1 var epsilon cos E. The Cartesian velocity vector can be trivially calculated as v equals mu a r minus sin E 1 minus epsilon 2 cos E. Display style math v equals frac sqrt mu a r left Langle sin E sqrt 1 var epsilon caret 2 cos E right wrangle. The important special case of circular orbit epsilon. Topic 0 gives theta. E equals m because the uniform circular motion was considered to be normal, a deviation from this motion was considered an anomaly. The proof of this procedure is shown below. Mean anomaly, m. The Keplerian problem assumes an elliptical orbit and the 4 points S the Sun at one focus of ellipse Z the perihelion, C the center of the ellipse, P the planetend, A equals C Z display style A equals CZ. Distance between center and perihelion, the semi-major axis, epsilon equals C S A display style var epsilon equals CS over A. The eccentricity B equals A 1 minus epsilon 2 display style B equals A sqrt 1 var epsilon caret 2. The semiminor axis R equals S P display style R equals SP. The distance between Sun and planet theta equals Z S P display style theta equals angle ZSP. The direction to the planet as seen from the Sun, the true anomaly. The problem is to compute the polar coordinates r, theta of the planet from the time since perihelion t. It is solved in steps. Kepler considered the circle with the major axis as a diameter, and x x the projection of the planet to the auxiliary circle y y the point on the circle such that the sector areas zcy and zsx are equal. M equals z c y display style M equals angle ZCY. The mean anomaly, the sector areas are related by Z S P equals B A Z S X. Display style ZSP equals frac B A C dot ZSX. The circular sector area Z C Y equals A 2 M 2. Display style ZCY equals frac A caret 2 M 2. The area swept since perihelion Z S P equals B A Z S X equals B A Z C Y equals B A 2 M 2 equals A B M 2 Display style ZSP equals frac b a c dot ZSX equals frac b a c dot ZCY equals frac b a c dot frac a caret 2 m 2 equals frac abm 2 is by Kepler's second law proportional to time since perihelion. So the mean anomaly, m, is proportional to time since perihelion, t. m equals n t. Display style m equals nt, where n is the mean motion. Eccentric anomaly, E. When the mean anomaly m is computed, the goal is to compute the true anomaly θ. The function θ equals f m is, however, not elementary. Kepler's solution is to use E equals z c x. Display style E equals angle ZCX. X is seen from the center. The eccentric anomaly is an intermediate variable, and first compute E as a function of m by solving Kepler's equation below, and then compute the true anomaly θ from the eccentric anomaly E. Here are the details. ZCY equals ZSX equals ZCX minus SCX. A2M2 equals A2E2 minus A epsilon A sin E2. Display style begin aligned ZCY and equals ZSX equals ZCX SCX frac a caret 2 m 2 and equals frac a caret 2 E2 frac a var epsilon c dot a sin E2 end aligned division by a 2/2 gives Kepler's equation m equals E minus epsilon sin E. Display style m equals E var epsilon sin E. This equation gives m as a function of E. Determining E for a given m is the inverse problem. Iterative numerical algorithms are commonly used. Having computed the eccentric anomaly E, the next step is to calculate the true anomaly θ. But note, Cartesian position coordinates reference the center of ellipse r, a cos E, b sin E. Reference the Sun with coordinates c, 0. Topic A 0 r. A cos E, a, b sin E. True anomaly would be arctan ρ, Rx, magnitude of r would be square root RR. Topic: True anomaly θ. Note from the figure that C D equals C S plus S D. Display style overwrite arrow CD equals overwrite arrow CS plus overwrite arrow SD, so that a cos E equals a epsilon plus R cos theta. display style a cos e equals a var epsilon plus r cos theta dividing by a display style a, and inserting from Kepler's first law r a equals 1 minus epsilon 2 1 plus epsilon cos theta display style frac r a equals frac 1 var epsilon caret 2 1 plus var epsilon cos theta to get cos e equals epsilon plus 1 minus epsilon 2 1 plus epsilon cos theta equals epsilon 1 plus epsilon cos theta plus 1 minus epsilon 2 cos theta 1 plus epsilon cos theta equals epsilon plus cos theta 1 plus epsilon cos theta display style cos e equals var epsilon plus frac 1 var epsilon caret 2 1 plus var epsilon cos theta equals frac var epsilon 1 plus var epsilon cos theta plus left 1 var epsilon caret 2 right cos theta 1 plus var epsilon cos theta equals frac var epsilon plus cos theta 1 plus var epsilon cos theta. The result is a usable relationship between the eccentric anomaly E and the true anomaly theta. A computationally more convenient form follows by substituting into the trigonometric identity tan 2 x 2 equals 1 minus cos x 1 plus cos x display style tan caret 2 frac x 2 equals frac 1 cos x 1 plus cos x. Get tan 2 e 2 equals 1 minus cos e 1 plus cos e equals 1 minus epsilon plus cos theta 1 plus epsilon cos theta 1 plus epsilon plus cos theta 1 plus epsilon cos theta equals 1 plus epsilon cos theta minus epsilon plus cos theta 1 plus epsilon cos theta plus epsilon plus cos theta equals 1 minus epsilon 1 plus epsilon 1 minus cos theta 1 plus cos theta equals 1 minus epsilon 1 plus epsilon tan 2 theta 2. Display style begin aligned tan caret 2 frac e 2 and equals frac 1 cos e 1 plus cos e equals frac 1 frac var epsilon plus cos theta 1 plus var epsilon cos theta 1 plus frac var epsilon plus cos theta 1 plus var epsilon cos theta 8 pt and equals frac 1 plus var epsilon cos theta var epsilon plus cos theta 1 plus var epsilon cos theta plus var epsilon plus cos theta equals frac 1 var epsilon 1 plus var epsilon c dot frac 1 cos theta 1 plus cos theta equals frac 1 var epsilon 1 plus var epsilon tan caret 2 frac theta 2 end aligned. Multiplying by 1 plus epsilon gives the result 1 minus epsilon tan 2 theta 2 equals 1 plus epsilon tan 2 e2. Display style 1 var epsilon tan caret 2 frac theta 2 equals 1 plus var epsilon tan caret 2 frac e 2. This is the third step in the connection between time and position in the orbit. Topic: Distance r. The fourth step is to compute the heliocentric distance r from the true anomaly theta by Kepler's first law. R 1 plus epsilon cos theta equals a 1 minus epsilon 2 display style r 1 plus var epsilon cos theta equals a left 1 var epsilon caret 2 right. Using the relation above between theta and e, the final equation for the distance r is r equals a 1 minus epsilon cos e display style r equals a 1 var epsilon cos e. Topic: See also circular motion, Free fall time. Gravity. Kepler orbit. Kepler problem. Kepler's equation. Laplace-Runge lens vector. Specific relative angular momentum, relatively easy derivation of Kepler's laws starting with conservation of angular momentum. Notes